Today we will be using Mathlink Cube manipulatives to demonstrate the standard 5.md.c.5c, which reads, recognize volume as additive. Find volumes of solid figures composed of two non-overlapping right rectangular prisms by adding the volumes of the non-overlapping parts, applying this technique to solve real-world problems. This manipulative can be really helpful in introducing this standard because it allows students a more tactile way of finding the additive volume of rectangular prisms. To begin, we will display two separate rectangular prisms as seen here. Using what we already know about volume, I can calculate each separate unit's volume by counting unit cubes or applying the formula length times width times height. Our first figure has a length of 3, width of 1, and height of 2. This gives us a total volume of 6. Our second figure has a length of 4, width of 1, and height of 2. This gives us a total volume of 8. If we know the volume of each of these shapes separately, we can make the assumption that when we connect the shapes together without changing their individual volumes, the total volume of our new shape can be found by simply adding their separate volumes together, 6 plus 8, giving us a total volume of 14. Now let's look at a different composite shape that's already been joined together. This time, the shapes have not been defined separately by color, which allows the students to find their own ways to divide the figure into two rectangular prisms. First, I might choose to divide the figures in this way, giving me two shapes that look like this. For shape 1, the length is 4, width is 2, and height is 2, giving us a volume of 16. Shape 2 has a length of 2, width of 2, and height of 3, giving us a volume of 12. Adding these volumes together gives me a total volume of 28. But let's explore another way to look at the same shape. Returning the composite shape to its original form, I can also choose to divide it in this way, giving me two shapes that look like this. For this example, shape 1 has a length of 6, width of 2, and height of 2, giving us a volume of 24. Shape 2 has a length of 2, width of 2, and height of 1, giving us a volume of 4. Adding these volumes together gives me a total volume of 28. Despite dividing the shape in completely different ways, I find the same composite volume. This illustrates that as long as I divide my shape into rectangular prisms, I can still find the total volume in an additive manner. For the last example, we see a composite figure made of 3 different colors. These colors represent 3 rectangular prisms I can divide the composite shape into. The first shape has a length of 2, width of 2, and height of 2, with a total volume of 8. The second shape has a length of 4, width of 2, and height of 1, with a total volume of 8. The third shape has a length of 5, width of 2, and height of 1, with a total volume of 10. If I add the volumes of all 3 shapes together, I get a total volume of 26 for the composite figure. Let's check this answer by counting the unit cubes individually. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. As you can see, we got the same composite volume by individually counting cubes as we did by applying this additive property of rectangular prisms. This illustrates for your students that no matter how many rectangular prisms we have to divide our shape into, you can always add each of the volumes up to get an accurate total volume. These are just 3 examples of how we can use Mathlink Cubes as an effective manipulative to demonstrate standard 5.md.c.5c. This is a highly effective tool to use to help students grasp the additive nature of the volumes of rectangular prisms. So check it out.